Today, we're going to be dealing with building on Starknet. We're going to focus on how to write Cairo smart contracts. This is the Blockfuse Labs Starknet Bootcamp. Today is May the 19th of May, 2024. My name is Abdul Samad Sadiq. You can call me OT. On Twitter, my handle is Otaiki Sadiq. Just drop a follow and I'll follow back, right? So let me move forward with the slides. So just before we continue, I just want to make some noise about the Starknet Hackathon. Hackathons are a really nice way for you to get your hands dirty with work. In my Web3 journey, hackathons were a very nice way for me to, build stuff and be more confident in my skills. So I'd implore everyone to, participate in the ongoing Starknet Hackathon, which is the Reignite Hackathon. It's happening from the 12th of May to the 26th of May. There are so many tracks with over like $3,000 in price. You could go sign up, just Starknet Hackathon Reignite, right? I will drop the link to that in the chat so that everyone could check it out. I'll drop the link now for everyone. So, the link is really easy. It's hackathon.starknet.org. There have been several sessions. We have done the getting started with Starknet ecosystem, the deep dive into Cairo ecosystem, and currently we are now here, which is building on Starknet, right? As I said earlier, I'm going to introduce you to Starknet smart contracts and, pretty much the difference between the regular Cairo programs and the Starknet smart contracts. So everybody should get prepared, get your editors open and your notes ready. So the topics we're going to we'll deal with Cairo programs versus Starknet smart contracts, functions and interfaces in Starknet, writing and deploying a simple storage contract, understanding events, traits, and syscalls, and cross-contract interactions and libraries, and modules and scope in Starknet. So let's talk about what smart contracts are. So at the base level, what a smart contract is an immutable piece of code which logic has been written by the programmer, right? So when you write a smart contract, the code can no longer be changed, except it's an upgradable smart contract, right? And because the code is visible on the blockchain, it means everybody can see it and they can trust and also verify that everything is working. So it doesn't mean it has its own smartness on its own. What that means is that you can always go through the logic yourself to be sure, which means that let's take a scenario where someone writes a smart contract that is to perform a certain function, right? And the person builds a client side and says, oh, interact with this thing and you get this action done. What you should do as someone who has knowledge of smart contracts is that you're able to go through the smart contract code to see and verify for yourself, right? And as smart contract programmers, it's essential that we make sure that we write codes that are really accurate, because one of the pitfalls of smart contracts is the logic error, right? And the error from the programmer when maybe they do not perform, they do not enforce certain rules properly. So it is it's a very big deal for us to ensure that we write code that is really good and ensure that our code gets audited. So smart contracts are programs that run on the Starknet operating system, right? So typically when you have your Cairo programs are usually written in Cairo, but they are not tied to the blockchain, right? They run on the SVM and they can be used for off-chain computation or proofs, which means that your regular Cairo program, you can use it for off-chain, you can use it for computation, you can use it for proofs and all that, but they are not tied to a blockchain, right? Which means your regular Cairo programs would run normally and there won't be any issues with it, right? You could use it to do things that are not blockchain dependent, right? But then what Starknet contracts are, Starknet contracts, on the other hand, they are Cairo programs that are designed to run on Starknet, right? So this gives you access to different blockchain specific features, right? You'd have access to storage, events, system calls, and all things that are usually native to blockchain. So what the Starknet contract does is that you are should I say abstracting what the Cairo program does, and then you're now using it for blockchain purposes, right? You could look at some of the key differences between your your Cairo program and your and your regular smart contract, right? So for your Cairo program, you could do general computation with it, but for your Starknet contracts, you'd have to focus on blockchain logic. For your Cairo program, there is no persistent storage, right? When we talk about persistent storage, we're talking about let me give you an example, right? Let's say you write a regular JavaScript program with your regular front-end technologies, right? You notice that whenever you refresh your page, that storage has gone, except you're making use of like local storage, which means that there is no persistence in the program storage, which is similar to Cairo, right? Cairo itself doesn't have a persistent storage. But when you now go move over to the side of the Starknet contracts, you now have what we call persistent storage variables, which means that whatever state variable that you implement, that storage is persistent, which is what gives you access to be able to store data on these storage variables. So that's pretty much the difference between the storage levels for Cairo programs and Starknet contracts. Then for the execution context, Cairo programs, they run off chain, whereas Starknet contracts run on chain, which is on the Starknet network, right? So when you mean that it runs on chain, it means that like that execution is run across the network and all the nodes that are participating in the network. So Cairo program has limited system calls. That's syscalls. They have limited syscalls or virtually none. Whereas for Starknet contract, they have access to different blockchain syscalls. And for deployment, your Cairo program is not deployed to a blockchain. So your Cairo program is just a regular program. It's similar to, let's say, when you have like a Rust program, right? It's not deployed. It's just compiled, right? But then for your Starknet contract, you can deploy it and then you deploy it as a contract. So when it's deployed as a contract, you get an address. And that address is how you are able to like access the different functions that you have defined in your Starknet contract. You can modify the state variables and you can also read the state variables, right? So you'd find out that like in your regular Cairo programs, you'd have like a main entry point where there's like a main file. Whereas for your Starknet contract, it's more or less like how you'd have like different modules. And then these modules are now packaged and deployed on the Starknet blockchain, where we can now access we can either decide to read the variables in it, or we can decide to write to the variables in it, depending on the functions that we have defined in our program, right? If we like go back now, we'd see. So I mean, you'd want to know what the structure of a Cairo contract would be, right? Of a Starknet contract, sorry. How is it like? What's the dichotomy? How is it branched out, right? So when you have a Cairo, a Starknet smart contract, you'd have your smart contracts are typically written in Cairo, and a class is declared. So this class hash, this class that we declare, you could kind of like view it somehow like a blueprint, right? A blueprint of the code you have written, right? It's kind of like a blueprint of the code you have written. So this blueprint of the code is now from that blueprint, that class hash will now change anytime we make any modifications to the code, right? So that class hash is how it's like, should I say, we could call it like a snapshot of the code you've written. It's a snapshot of the code you've written. I mean, before I still proceed, I'd really encourage everyone to ask questions, drop questions on the chat so that we'll make this class as interactive as possible. So your smart contracts are written in Cairo, and there's a class hash that is generated whenever the contract is, declared, right? So you'd have your code, which is written in Cairo compared to Sierra, right? And there's also something called an ABI. An ABI is the application binary interface, right? And it is the one that shows us what functions are accessible, what type of functions it is. Is it a view function? Is it a write function? You understand? So what the ABI does is you could call the ABI like a map, right? A map as to how everything is implemented in our Cairo smart contract, right? And as I said earlier about our class hash is, it's like a blueprint or a snapshot of all the code we've written, right? So from this class hash, we could now make several deploys of our smart contract. Let me check the chat if there's any questions. Someone asked if we could get the slide. Yeah, sure, you could get the slide. I'll drop a link to the slide after the class. I see a couple of people have AI assistants, which are really nice. So let's go on. So the next thing we'll talk about now is a the contract basics, right? What are the basics of a Cairo contract? So at the base level, what a Cairo or a smart contract is in Cairo is a module, right? It's a module. But then there are definitions, or should I call them macros? These macros are what tells the computer or the machine that this is a smart contract, right? So it must, sorry, so as I was saying, yeah, so these macros are what tells the machine that this is a smart contract. So you can see this macro that is written here, which is, I think I'd have to like annotate this so that, you know, everyone could see. Oh, can you guys see my mouse? Exactly here. So this macro here is what tells it that, hey, this, what I'm writing here is a smart contract, right? And as you notice, all our smart contracts are modules. They are modules in Cairo. So they must have the mod keyword at their front, followed by this, which is the name of the contract. So this name of the contract is what you use to like know that, oh, this is the name of my contract. So I mean, it's important that you ensure that you have like the name of the contract, name of the file, name of the contract should also tally with the name of the file. So a very important thing, if you notice when I was talking about our smart contract, I mentioned something about persistence, right? When I was explaining the key differences, I said that in smart contracts on Cairo, the storage is persistent. So one of the things that make that storage persistent is this storage macro that we put here, right? And it says that we put our struct as a storage. So a smart contract must have a storage defined, even if it's empty. The reason being that, I mean, as we said earlier, the key difference, which is the persistent storage, this storage is what must be defined, right? This is where we define all the storage or the key state variables that we would be using in our Starknet smart contract. So it's very important that when you are defining your or creating or writing your smart contract, you ensure that you have your storage defined and you also have your macro that defines it as Starknet contract. I mean, if I just write this as a regular model, it doesn't qualify as a contract because it doesn't have this macro. So adding this is what now tells the virtual machine that, hey, this is a smart contract. So next thing is, yeah, constructor. So if you've had experience in object-oriented programming, you know what a constructor is. But constructors are typically called once when the contract is deployed, right? So at every point the contract is deployed, the constructor is the first function that is called, right? The constructor is the first function that is called, and it must be called constructor. I mean, you can't go and give your constructor a different name. It must be called constructor, and it must also be annotated with the constructor attributes. A contract cannot have more than one constructor. Yes, so that means every code that you want to write that should be initialized should be written in this singular constructor. So remember, you must have this constructor attribute, and it's deployed. It's only called once, right? So what this means, and I want us to have this in our frame of mind whenever we are thinking about programs like this, right? We should note that, okay, I mean, I want to make sure that we have the right mental model for what constructors are used for in your contract. So let's say you'd want to initialize something that should only be initialized on deployment. That would be something like setting default values or setting access controls, right? Things like that, or making initial transfers or something to kickstart the whole contract operation, right? You want to initialize default values, you want to either you want to initialize default values or you want to, you know, make certain access control settings in your constructor code. So that's part of the things that you put there, right? And remember, a contract cannot have more than one constructor. So the next thing we are going into is exposing functions, right? So to expose functions, we have, so to expose functions, you'd want to expose the functions that would be accessible. So before that, let me explain the two types of functions on our Cairo. We have the read functions and we also have the write functions, right? The read functions, which are views, they take a snapshot of the state as parameter. So read functions are typically free and do not take any gas, right? Read functions do not take any gas and they are free. So once you call the read function, there is no gas that is taken from the contract and it's a free call. Whereas for the write functions, the write functions usually take mutable reference of the state. So it costs gas. Because of that operation, that is one of the reasons why it costs gas to call. So for write functions, you have to be sure that the write function doesn't, the write function is always going to cost gas for it to be able to work as it should. So remember, another thing you should know is that all public functions usually take self as a first argument. So for people who are coming from the background of object-oriented programming, they understand that when you have functions that you define inside the class, you'd have to make a self-reference, because that self is like you are making a reference to the state of the general object, right? So as I was saying, remember, our read function is taking a snapshot of the state. That is why we have this at that is put here. Whereas for our write functions, we are having a mutable reference, which is taken, which is why we have this ref keyword that is included here. Next thing we're moving into now is interfaces. So what is an interface, right? An interface is a way for you to like list out all the attributes that a contract has, right? So your interface ensures that any contract that is implementing this interface will expose the given functions and the type safety. So it's used to standardize how the contracts are called. It's not really mandatory, but it's better because it allows you to have a better integration with the existing tools and the DApp at the same time. So when you are defining your interfaces, you'd want to add this macro, which is the Starknet interface macro. With this macro here, this is how you're able to tell the compiler that, oh, I'm creating an interface. A best way for me to define this interface is like, oh, you've created your program, right? But you want to create like a map to like show, oh, these are all the available functions on this contract, right? So that's pretty much how it is. So when we have this kind of like blueprint to show that, oh, this is all our this is all the functions that can be called in our contract, right? Then we can now, it now enables the person that is integrating it to have like a base to which they can make calls to our contract. Pretty much that's what interfaces do. So from interfaces, so I mean, there are two ways of calling an interface. You could either call it like explicitly, or it could be called implicitly, right? So when we are explicitly defining an interface, you'd have to write it like this, where you'd have your macro and you'd have your inside the same file, you'd have your like explicit interface, where you specify the function names and their return values, right? If you notice, we have the implementation of this interface here, where we have this the get value function and the set value function here, which are like implementations of what is in this interface, right? But you notice that what we just got from here is that we got the function name, we got the argument it's going to take. But in this case, I mean, for every function, you know, we have to pass in the contract states before the other arguments, but then followed by the return value, right? And when we define it in our interface, we did the same thing for the get value and the set value, right? We specified it here, but we did not put any like scope or code block, because you don't put code blocks in your interface implementations, right? And so the ABI embed v0 macro, it enables for the functions to be called externally, right? By doing this, we're able to say, oh, these functions now are public, right? There's functions that can be called externally and people can make reference to those calls, right? So from there, we now have the implicit interface. So the implicit interface, for you to use the implicit interface, you need to, so it's very important you make the annotations, right? You have to use the annotation, generate trait, and this ABI per item. So that's like a way to make sure that the thing is implicitly generating these interfaces for us, right? So that's it with implicit interfaces. But it's very important that you note these two annotations, right? This generate trait and this API per item, because I want you guys to note the two differences here, right? You can see that here we have what? We have the ABI embed v0 here, but that's for the explicit interface definition. Whereas for the implicit, we have what? We have ABI per item and the external v0, right? So always note your annotations, because your annotations are really, really important in your Starknet smart contracts. So the next thing is events, right? Events. So The best way for me to explain events to you are, let's say you have a program, right? And you want to be able to log data, right? You want to be able to say, hey, this something happened when this person did this. Something happened when this person did this, right? It's a way of keeping track of everything that's happening in your smart contract without. So typically, let's say you have a function that changes states or updates a state variable, right? When you update the state variable, how would you know that the state variable has been updated, right? Would you have to go and be looking at all the transactions and trying to filter the transactions to find out at what level was this function called, right? So the most efficient way for you to do it is with events, right? So events are similar to on your back end when you log data on your typical backend servers, right? Where you create logs and stuff like that. So you can have your custom. So events on their own are their custom data structures emitted by a smart contract during its execution. So you could index the key, and when you index the key, this allows for a quick search when you are querying the blockchain. So when you have events in your smart contract, it's advisable that for every state changing function you create, there's an event that follows it, right? I mean, you won't want to put events in a view function, right? Because it's just a view, right? But for state changing functions, which are like really important, that shows that changes has been made to state, you have to emit an event. So when you emit this event, you are like signaling the blockchain and saying, hey, guys, this is someone just transferred ownership. That's in the case of what we have here, right? And when you have events and you're emitting events, you'd want to be able to index this data. So you could either index it manually, like with your Starknet JS, where you'd be listening for those events, or you make use of data indexing solutions like the graph. So I have a tutorial video where I talked about how to index data on the blockchain, on Starknet blockchain, using subgraphs and substreams, which are really efficient ways for you to index data, right? So how do you define an event in Starknet, right? So for you to define an event, you'd have to use this event macro here, and you'd use this derived drop then Starknet event. So you specify with an enum the event, followed by the name of the event, followed by a reference to the struct that has what the event is. So when you now come over and you define what the event is going to contain, remember you are defining what the event is going to contain. What the event is going to contain, meaning the data you want to emit. So let's say we have we transfer funds between two users, right? If we transfer funds between two users, the event we want to emit now, for example, is the name of the person that is sending it, that's the sender, the receiver, and the amount that is being sent, right? So when we do this, we'd have to define that in our struct for our event. When we do that, then we could now listen to it on our subgraph. So when we listen to it on our subgraph, we now have like a way for us to be able to pass it back into our front end. Another typical or good example of events is let's say, for example, on your Uniswap. So whenever people swap tokens, you see that they highlight that also token has been swapped, and that also provides like a good way for you to make sure that your events have been emitted. So the next thing we're going to talk about is dispatchers, right? And what dispatchers are, they are automatically generated from your interface, and using a dispatcher, the function is executing with the storage and context of the targeted contract, right? So when you make use of a dispatcher, it's more like as if you are referencing another contract, right? You want to reference another contract and make and reference like the storage the storage and the context of the contract that you're targeting, right? It's just like we both have, should I call it more like an API call between the two different contracts, right? You're making like API calls to another contract, or you're making like a call to another contract, basically. So before we continue, let me check the chat to see if there's any questions. Oh my God. I'm seeing I'm too fast, so I would slow down a bit. I would slow down. But I mean, if there's any place that you have any confusion, could you like raise your hands or state this part so that I would okay, someone said they are still confused about the dispatcher. So as I was saying about the dispatchers, right? Automatically, your dispatchers are automatically generated from interfaces, right? And dispatchers are enabling you to execute with the storage and context of the targeted contract, which means that we are like, it's like we are making pointers to another contract, right? So because of the interfaces that have been generated, right, these interfaces are exposing, okay, let me go slower. These interfaces are exposing us to several functions that are available in that contract. So now you see the importance of interfaces, right? With an interface, you've exposed the functions and stuff that are available in that contract, right? So now with the dispatchers, and what you are now doing is that you are calling, or should I say, you are now saying, hey, this is get data and set data that is available in this contract, right? I want to get the data in that contract. So how do I get the data in the contract? I'll now create another contract, and then this contract that I've created can now make calls. So this contract I've created here can now make calls to this contract through the dispatcher. Does that make it clearer? So after that, we'll talk about what like components are. So components are modular. Oh, I forgot to, mention how you can introduce it. So you are referencing this, as you can see, this import here, where we're using this data dispatcher and the dispatcher trait. So with that, we're able to like call the variable here and have put in the contract address of the contract that we um want to reference, right? So if you notice, you can look at the code clearly, you see that we have defined dispatcher here, and we use this data dispatcher to tackle, to like make a reference to the contract, right? So that means this contract called data is probably already deployed, right? So all what we just need is the contract address of this deployed data contract, right? And from there we can get the data that is stored in it. Yeah, similar to delegate call and call instability, yes. So next is components, right? So components are modular add-ons containing functions, storage, and events. So you can implement them in multiple contracts, but they cannot be deployed or declared. It just becomes part of the contract bytecode. So when you have a component, you know that you cannot deploy that component. It looks like a contract, it feels like a contract, but it's not a contract because you can't deploy it, right? So it's just like a way for you to compartmentalize your code, right? So if you notice, one of the key differences between your contracts and your components is that the macro for your components has this component here instead of like contract. So that's a very key difference. I think the last thing I was going to talk about here is syscalls, which are like native calls that are available to the Starknet blockchain, right? So like things like you want to get our address, you could kind of like compare syscalls to, for people who have experience in Solidity, you can compare it to like when you do like tx.origin or msg.sender. So syscalls are like those things that are native to the Starknet blockchain that you can call in your contract, right? So there are several syscalls available, which you can see if you check the documentation. So, I mean, before we move on, I'll talk about the different use cases, right? So there are many use cases for smart contracts. There's DeFi. So for DeFi, you'd have to set like the several kind of rules that would apply to whatever financial system you are building with your program. So remember, with DeFi, you have like a program that is performing things that are finance related, right? So smart contracts are like the basis of any DeFi system you see, because people can trust that the code is immutable and can no longer be changed. So everybody sees the enforcing rules and they can trust in the system. So the basis of smart contract again is trust, right? Everybody trusts the code because they know that the code cannot change and they can all see and read the code. Compared to like your traditional financial systems, because with traditional financial systems, I mean, we cannot see the code of UBA Bank. We don't know what is happening behind the scenes, right? We just have trust that UBA is not going to carry our money and run, something like that. But with DeFi, you are seeing the code, you know what is happening with your money. You're able to track everything, you're able to read through the code. And with bug bounty programs and auditing programs, if you find a fault in the code, you can even report it. So it's like an ecosystem that you are fully part of. On-chain games, so for token distribution, for game points allocation, we're having transparent, readable code that everybody can see and everybody can trust, right? Which makes it way better than whatever existing system. So in the case of governance, we have DAOs, which are decentralized autonomous organizations, right? These organizations are meant to function without any centralized entity holding them. And what other way would be best to do this than smart contracts? Smart contracts allow you to be able to set the enforcing rules for whatever organization and community you have. This allows everybody to have access and see what is happening, and they can trust in the code and not have to rely their trust on, let's say, the president of the association. The association is decentralized, there's equal power and equal opportunity. Even the whole Starknet ecosystem also works with a DAO, because most recently we voted on proposals that it's our vote, all of us that are participating in the system, that allow them to make changes on the ecosystem. So wallets, because wallets are using the smart accounts, they're also very dependent on smart contracts for royalty sharing, decentralized identities. The use cases for smart contracts are much more. And I'm even looking forward to seeing people create and draft newer use cases for smart contracts, because the possibilities are limitless and endless. So some of the popular ones is Ekubor, Argent, Realms World, Nostra. These are all different use cases of smart contracts that have been implemented. So let's all take a break. As we continue, we'll just be having a workshop where I would, explore most of the concepts that we've already talked about. I'll show you how to deploy a contract, and we'll talk about like most of the things that we've talked about, right? We'll see it in code. I mean, talk is cheap. Show me the code. So enough with the cheap talk. Let's get coding. So I'm hoping everybody already have their dependencies installed. They have their ASDF, Scarb, Starknet Foundry, Rust. One of the things that helped me, I think, was I used Starknet for my installation, which made it like really efficient for me. Also, you also have to have Starkly installed for our deployments. I'll be referencing an article for our deployments and declaration, which is like a very efficient article. I'll share the link to that article. And I also have a hackmd file. Yes, I also have a hackmd file that I would share at the end of the class, which kind of like covers most of the stuff that we are going to do in the coding part. So let's get ready. Live coding. So that I could get up to speed. So I'll just navigate to my documents directory before I start. So to initialize it, I'll do scarb. I'll do scarb new. So what we call this? Let's call this learn Starknet, right? So it asks you what test runner do you want to set up. Pick Starknet Foundry. Okay. So if you use uppercase letters in your package name, it causes problems. So you'd have to change that. So I'd use what? Scarb new, learn, Starknet like this. So let me make my font a little bit bigger so everybody can see it. So yep, you pick Starknet Foundry and it spins it up for you. So you can see it has created the package. Then now we could CD into it. When we CD into it, we will do code to have a Visual Studio Code. So if you can you guys see the Visual Studio Code? Please react with a thumbs up if you saw the Visual Studio Code. Okay, we're on track. So once you spin this up, you'd see your source, you'd see your live.cairo, which has like a dummy contract in it. You could see some of the stuff that we've already talked about here. You can see here, they have an interface and it is defined with this Starknet interface macro. You have the interface which exposes the functions that are possible, that are available in our contract, increase balance and get balance, right? And we can see the implementations here. I see the increase balance implementation and the get balance implementation, right? So, I mean, before we proceed, we can see that we have, just give me a minute. Okay, so before we proceed, right, I want to show something, right? So let's say, typically, let's say we have some sort of, so once we've set it up like this, we'd want to do scarb build to be sure like everything builds as it should, which is just to know if like everything is working well. You could do scarb build, yeah. So we are sure that everything is building as it should, which means our environment is ready, right? So before we continue, I want to, reference something, right? So typically, when you were learning Cairo before you got exposed to Starknet, you'd see that we'd have, okay, I think someone's hand is up. Whose hand is
Yeah,
up?
please can you zoom in
Oh, on the
the
VS Code. Okay, I'll do that now. Is it better now?
yes, yes.
Wonderful. So, okay, so now, typically, you'd have your regular Cairo program like this, right? We'd have a function, and our function will perform a certain action. We'd have the function code like this, and when we run this, we'll be able to like run our typical Cairo program this way, right? But now, when we are dealing with our Starknet programs, which are much more different than this, we would have for our Cairo program, for our Starknet programs now, would have so let's say we have this prompt, that's this Cairo program here, which is just a Fibonacci function that will take in a number and it will do what like you do with Fibonacci series, right? Which would be like an extension of the number, adding it up from, let's say we have a number 10, it will do 10 plus 9 plus 8 plus 7 and up to like the end, right? So if we were to do that in a regular Cairo program, it will look something like this. But let's say we have to convert this code now into a Starknet program. It will be much more different, right? Because with a Starknet program now, we're going to be storing our result on chain and we have like so many other things that we have to implement. So for me to do that, I will decide to let me comment this out and convert it to a Cairo program so that we all like follow through together the process of converting to a Cairo program. So for the first thing we want to do is that we'd want to set up our macro, right, to show that this is a Starknet program. So to set up our macro, we could have our macro for this to be what Starknet contract, right, which tells our compiler that hey, we've got our Starknet smart contract here, right? Then the next thing we want to do is to define our contract. And to define our contract, we use mod, which specifies that it's a module, followed by the name of the contract. So in this case, we'll do mod Fibonacci contract, right? Then when we've done that, so I want us to pay attention to some key things here, right? We have in our Fibonacci contract, we're expecting a result at the end of it, right? And apart from expecting a result, we have a function. So this our function is like to perform the Fibonacci, and we could have another function to do the cool computation and give us and store the result into our storage, right? Because we want to make sure that we're able to store the value that we get when we perform the Fibonacci. So if it's a smart contract, right, we'd want to make sure we have this. We want to have what is central storage, first of all. The central storage, right? We want to have a central storage for the current Fibonacci number, right? We'd also want to have a function to view what the current Fibonacci, to view the current Fibonacci results, right? Fibonacci results. So this should not be number, it should also be results, right? And then we'd also want to have we'll have a function that performs the Fibonacci itself, right? We want to have a function that performs the Fibonacci and calculation, right? I want to have a function that stores our Fibonacci results. So now we have a couple of things. So it's essential. I feel like when you're writing Starknet smart contracts, that you're able to like write it down and break down everything that you need to do. So by the time you're able to break down everything you need to do, it helps you to have a proper frame of mind for the contract you want to write. So once you are able to break this down, you say, oh, I want to make sure I have a central storage for this, a function to view, a function to set states. So you notice now, what do we have? We have a function that we are setting states. We have a function for reading states, and we have a function that just does computation, right? You see how we have been able to break this down? It's okay. Truth, your hand is still up. Do you have something you want to say? Okay, truth. Okay, that's an old request. So we've been able to break down all the key things for us. So we are going to get into coding. I always say that writing the code is the easiest part, right? The hardest part is how you're able to frame your mind. you have to frame your mind to work in a certain way to understand how the code would work. So we remember what we are doing again is we are converting this Fibonacci code here into a Starknet smart contract. So move on, right? So now the first thing we want to do is to set up our storage. If you remember correctly, we said that if you are going to write a smart contract, you should, always put storage, your storage annotation, right? Before you then go ahead to create the storage struct. So it's inside the storage struct that would have all our state variables. And our current state variable is going to be what? Our state variable. So let me carry this, our comment here, and then I'll put it up at the top here, right? So inside the storage, we can now put it as what? Results. And what we're expecting with this, our result is what? In an unsigned integer 32, right? We're expecting a number, right? So now that we've gotten our storage, which is our central storage, I think the next thing we'd want to do is to have a function that performs our Fibonacci calculation, right? We want to have a function that performs our Fibonacci calculation, or yeah, a function that performs our Fibonacci calculation. So for us to do this now, we create the function just like we typically would with Cairo. So because this is not going to be a function that is going to be exposed, right? It's just a function that we have inside, right? So it's going to be a function, we can call that function Fibonacci what? Calculator, right? We're expecting to take what? A number, and the number it's going to take is what? A U32, right? And this number should return a U32 when it performs the calculation. So once we've gotten that right, the next thing we want is to set the logic, right? So we could just go up here to look at the logic we have here, copy this logic, and paste that logic here, right? Because we're just converting a regular program into a Cairo program, right? So we can have it like this. In this case, we are not using n, we're using number. So we are returning number. So if the number is less than or equals to 1, it should return the number. Else, so this is I forgot what they call this. Oh god, there's a name they call this where you have it repeating consistently. So okay, someone has said it. Okay, yeah, Truth, what do you want to say?
I said recursion for
yes, it's called recursion. Yes, so we have it as a recursive function, right? So because it's a recursive function, we are sure that it will keep on running till it gets to this base. So remember, this is our base statement, and when it hits this base statement, everything ends, right? So we could have it like this, Fibonacci, but like Fibonacci is supposed to C, so we just fix this here, right? The Fibonacci n minus 1. So no n here, so it's what? Number. Then we have what? Number. Okay, so I put only one n instead of an extra n, and voila. So we have a function now that performs our Fibonacci calculation. We are done with that, right? So let me kill this. So now the next thing we want to do is a function that will store this our Fibonacci result to storage, right? So now to have a function that will store this thing to storage, we could just, function that stores our Fibonacci result, right? So to do this, we could have another function, and we'll call that function store Fibonacci. No, we can call it compute and store, right? So what compute and store does is that it will make a computation, then store it, right? But compute and store would also take in the number. Compute and store would also take in the number that is going to go through the whole Fibonacci process. So remember, this compute and store is what is going to be exposed to the user, meaning it's a state changing function. And remember what we said in the slide. We said with state changing functions, you have to add a macro, an annotation to it, sorry. And the annotation you're adding is what? External what? V0, right? By adding this annotation, you're saying, hey, this function is going to be exposed. It's a state changing function, right? So what it will do now is, and remember we said for state changing functions, they take in a reference, which is like a snapshot of like the current storage. And when they do that, to them a ref, self takes in the contract state, and then it also takes in our number, right? Which is going to be what? A U, an unsigned integer 32, right? So now, what is it going to do? It will first of all get us the result. How does it get us the result? It gets us the result like this, right? Passing what? Fibonacci calculator, and we pass in the number, right? Then after that, we want to write to state. So remember, we also said in our slides that to write to state or to perform anything that is going to change that storage or to read from that storage, we have to use the self keyword. This is a practice that is very common in object-oriented programming, right? So it will be self dot. Remember, what did we use to store this our state variable here? We studied with what? Result, right? So we are writing to this result. So it will be self.result.write, right? Self.result.write. But what we are writing is this our what? Underscore result here. So when we do that, we should be able to compute and store. But now you see that we have a new error, right? And what this error is telling us that the method write is not found on our type, Starknet storage base. We are advised to import one of the following: Starknet storage and storage pointer access. So for us to be able to perform these read and write operations, we have to import something. So when you are importing things that are in the scope of your contract, inside your contract, you do what? Use, followed by the whatever it is you're importing. In this our case, we're importing Starknet storage, right? And we are importing what? Right. So we are making a write operation. We need to import from Starknet. So whenever you have core and you have Starknet, which means we are importing a module that is native to Starknet, right? So we can import what? Storage pointer what? Write access, right? With this storage pointer write access, we are able to make what? We're able to do what? Write operations on Starknet, right? I forgot to put the semicolon here, and because of that, now you see that we no longer have those red squiggly lines here. We're able to make our write operation. So now we've been able to do a function that stores our Fibonacci results. So because we're going to have another function that we're going to be exposing outside again, which is not an internal function, right? We'll use our same annotation, which is the external v0, and we can now create a function to view the current Fibonacci result. So to do that, we can just do it like this. So it's similar to what we do with our write, but except that the fact that we're not changing any state here. So we have a function, we can call it get results, right? So get result will always return a result. And what it takes, unlike the write function, it takes self, right? And then it takes a snapshot of the current state like this. And then it returns what? An unsigned integer 32. And then we can now have what? So either you do it like, no, I'm not doing this way. So we could just do self dot. We'll look at this, our storage state variable here, result dot read, right? So I want you to note something, right? Note that I'm not putting any semicolon at the end because I want it to return whatever it is reading, right? That is why you not put any semicolon at the end. And it's still showing us these red squiggly lines because for us to perform read operation, we need to import what? The storage pointer read access, right? By the time we're done, you can see that we have been able to, create a contract that reads and writes to storage. We have converted this our Fibonacci code here to an on-chain Fibonacci contract, which means everybody anywhere in the world can just get that contract address and perform Fibonacci using our contract. I mean, this is the most basic use case of a Starknet smart contract, but it's just a way for us to be able to demonstrate and practice what we just finished talking about. So we've been able to get functions that view, that reads, that stores on our contract. So I'll save this now and and that's it. So we would have to test to be sure that this our contract works. So for us to do that, we'll do what? Scap build, right? And by the time scap build, you see that we have no errors, right? So because we've not gotten to the stage of declaring and deploying, I'm just going to leave it at this for now. So the next thing I want us to also touch is, but before I move forward, let me check, is there any questions? Any question? Anything anybody wants to raise? So the typical workflow, if you have written your smart contract on Starknet, is that you'd write tests. So what these tests are supposed to do is that your tests are supposed to call the functions in your contract to verify and test for different edge cases. It's just like with Solidity, when you write your smart contracts in Solidity, you don't write the Solidity test, to accompany it, to be sure that, oh, I wrote things well and everything is working as it should, right? Because when you write smart contracts, your entry point or the way you can be able to access it, apart from tests, is when you deployed it and you have that contract address. So that contract address now acts as the way, or should I say the gateway, similar to how you have like an API URL. It now acts as the gateway for you to be able to access and interact with your contract. So the next thing we're going to do now is we're going to move to what functions and interfaces in Starknet. So we're just going to do like another practical demonstration of it. So permit me to comment this code. I'll comment all this code like this again. And we move, right? So after I've commented this code, so normally, okay, but since that is not the scope of today's class, I would have shown how tests would normally work. But so the next thing we want to do is to define a contract with functions, and we want to like create interfaces for it, right? So, I mean, what I'm thinking is, I'm going to drop a contract that I have written prior, and we'd like analyze it, see what the contract is doing, then we'll create an interface for the contract, right? So I'll just copy the contract and I'll paste it here, right? So we have this contract that I've written before. Let me remove this clause since it's the latest versions don't require it, right? So we have this contract, right, which is a counter contract. Pretty much what the counter contract does, similar to how our Fibonacci worked, was that we have, am I going too fast? If I'm going too fast, please react with a thumbs up. Okay, James, whoa. James has been waiting to say this for so long. Everybody has been waiting to say this for so long. Okay. So let me slow down a bit, right? So at any point in time, please ask questions. So we're going to, let me explain how this contract works, right? So we have a contract, a counter contract, right? This is our contract, our counter contract. We have specified the macro that specifies that this is a Starknet smart contract, right? After specifying the macro, when we are writing our Starknet smart contract, the next thing we are going to do is to use the mod keyword to specify that this is a module. Remember that in Cairo, contracts are what? Contracts are modules, right? And so because it's a module, we'll put the module and the name. So this counter now acts as the name of our contract, right? We now have counter as the name of our contract. So after we've been able to define our contract, the next thing we want to do is to import the modules, the core Starknet modules that allows us to be able to what? Read and write, to perform what? Read and write operations. So to import that, we're importing what? The storage pointer read access and what? The storage pointer write access, right? Once we import these two things, we now have a what? We now have a storage. So I'm also going to share a link on the chat to the hack MD file that I'm using, which is what I wrote for the class to make the class easier and better to understand. I'll call it what? Starknet development tutorial, right? I'll publish it now and share a link to it. So I'll share the link now on the chat. Right. So I'll share the link on the chat, right? So now I said that we have to import the Starknet modules that we would use to read and write. So these Starknet modules are the ones that allow us to have access to read and write operations for our smart contract. After we have imported these modules, then we go on to define our storage variables. Remember I said that one of the prerequisites for creating a Starknet smart contract is to ensure you define your storage. Your Starknet smart contract is not a smart contract if you don't define storage. And even if your contract would not make any use of storage, you have to define storage because it's the prerequisite for the contract. So when you define the storage, you use this your storage annotation here. And after you've done that, underneath it, you have a struct. Yeah, use your storage attributes. Sorry, it's not annotation. Use your storage attributes. Then you have the struct keyword storage with a capital S. So whatever you put in this struct would be what will be stored in your smart contract, would be the state variables. And for this counter contract, we are storing something called count. Count is the number that we are going to be counting as the counter contract implies, right? So now, what comes next is we have an external function. This external function is how we are going to increment this count. For us to increment this count, we need to have an external function to increment it. Typically, it's similar to how we had a function here to what? To store our Fibonacci results. But here we have a function that changes the state of this count function. So we all understand that this increment function now, because it is going to increment count and modify state, it's going to what? Consume gas when the user calls it. Gas is when you pay the token for the transactions that you are making. Because for you to update state, it's a transaction because you are changing how the blockchain is, right? So now, what we do in this our increment function, remember I said for every state changing function, we must use this ref keyword because it enables us to have like a reference of the contract state. Then we are able to read the current state of our account. For us to read it, what is making us have access to this read function here is because we're able to import this storage pointer read access, right? So then we get the current state by doing self.count.read. As I mentioned earlier, if you come from an object-oriented programming background, you'd understand that using the self keyword enables us to know that we are dealing with the current state of that program, right? And we get the count because the count is what we are using to define our current count at the point in time. Then we read it and we get it. So let's assume, because at any point in time, the initial value of this will be 0, right? So when we get the 0, we now write that the current state, we add 1 to it, then we write into it. So we updated this state here. So this function typically would cause gas for it to be called. The next function we have is a function to read count. And as usual, we use the external because it's a function that we are making public to the user. Remember, for internal functions, we do not add this word, we do not add this attribute because it's internal, right? So you have a function called getCount. And remember, for read functions, we're not using ref, but we're using it in this way. This was like a mutable reference, right? Then it's returning what? An unsigned integer 64. So what we do is we do self.count.read. So because if you notice, there's no semicolon and there's no return keyword. So because of that, it automatically returns whatever it reads. We then have an internal function that is not callable externally. So what this function does is that it just checks if it is positive. There is no need for you to make this function external because there's no use for it, right? But it could have uses inside our contract. So for that, we just use it in this format. We do not put this external attribute here, and because of that, it's not accessible externally. Are we in sync? If we are in sync, let me see thumbs up. Okay, thank you, Truth. Thank you, Judith. So let's move on. So now what we are going to introduce into this our contract is we're going to add an interface, right? So how do we create an interface for this contract? Remember I said to create an interface earlier on, we have to use what? The interface macro. So for us to use the interface macro, we come to the top of our contract here and put it as what? Starknet interface. Then we use the trait keyword, trait, followed by, so one of the convention, right, when you're creating interfaces, you add an I before the name of the contract. So in this case, since the name of the contract is counter, we could use what? I counter, right? And then we pass in this as the reference to the contract state, T contract dot state, right? And then from there, we now go on to define our interface. Remember I said our interfaces is just the function name and what the function, the arguments that the function is taking. So in this case, we just copy it like this. You could just copy it like this. Then what? Paste it here as the first one. Semicolon, move to the next one. And come here and we do what? We get the second function, right? Internal functions cannot be added to your interfaces because they are internal. And our interfaces provide a way that exposes these functions to what? To our user. Right. So we're done with this. So another thing you also do, you could put this your interface in a separate file just to make your code more better. But if you're putting this in a separate file, one of the conventions is for you to save it as I and the name .cairo. So we could test this our interface with Starknet tests. But since that is not the scope of today's class, I'll just leave it at that. So this clearly defines how we can create an interface for a contract that we've written, and I'll see it. I'll save now, and I'll check if there are any questions. If there are no questions, I'll go into the next part of our program, right? I'm going to show you guys how we can declare and deploy our smart contract that we've written. So the process is very seamless and easy if you have Starkly installed, right? Starkly is a tool that makes it easier for you to deploy and declare. So I'm going to share, I want to share the link to the tutorial so that everybody could follow along, or you could make reference to it later on. So for that tutorial, right, because it has been a while since I wrote that tutorial, don't do the Cairo run. Instead, use scarp, just use scarp build, right? Don't do the Cairo run, and don't try to run it, right? Don't run it this way. Just don't use the Cairo run. Instead, just use scarp build, right? Promise, does that answer your question? Just use scarp build. And you'll notice that there are some, like the tutorial has, let me just update some stuff in the tutorial. Here is supposed to be Sequoia, so I'll just change everything here to Sequoia. Okay, so now I want to show you guys how we can deploy our contract, right? So we have a contract that we are going to call simple storage. We'll write it and we'll declare it and deploy it, right? So for our simple storage contract, let's go. So I'll modify this our counter contract. I'll comment it out, sorry. Comment it out. And let's start. So for our simple storage contract, right? As usual, we'll have what? Starknet. Then we'll have what? Contract, right? Then we'll have the name of our contract, which is what? Simple storage, right? Right. It's going to take in this our import here because we need it since we are going to be reading and writing into states, right? And when we've done that, we can now have our what? Our attributes called storage. We would have what? Storage, which would be like value, but here instead of the value to be 32, we use what? 256. For our constructor, we'd want to have a constructor too. Let me just clean some of this code. So this copilot can be very, you know what, I'll disable mine. So now, the next thing we want to have is our constructor, right? Our constructor, remember I said the constructor can only be called once, right? So for our constructor, yeah, for our constructor, which is going to be called only once, we would have it. So remember, your constructor should be defined with the word constructor, right? And it takes in what the contract like this, takes it in like, how is it showing yellow screen? Okay, let's continue. Okay, so we have it takes in our contract state. Remember, the constructor is pretty much changing state, right? So we now have followed by something called, we can call this initial, right? And it's going to be a U256. So this will now be the base value for this our storage contract, right? So we'll just write into it. You can just have self dot value dot what dot write and what passing was our initial value. In this case, initial, right? Putting semicolon to end it. And then after our constructor, we want to have a couple of external functions, right? We want to have the external function that we would use to update the state. We'd want to have the function that we would use to update the state. So for the function that will update the state, we can have a function which we call set value, right? And what set value is going to do is that it's going to update this value in the storage with whatever value we want, right? So you could just copy this, paste it here. Instead of initial, you could write what? New. Oh, wait, no, let's not call it new like that. Let's call it what? New val, right? And what it's going to do now is we're going to have self dot what? Value dot write what? New underscore val, right? Then we could now have another function which we could call what? Get value, right? Get value. Get value doesn't need to collect a ref. What it's just going to take is ourself and what? A snapshot. We don't need to pass in any new value. All it does need to is self.value dot what? Read. And we are not passing in anything inside, right? Simple. So we already have our simple storage contract. And so we could just save this. After we've saved it, we want to compile our contract, right? So I'll make this edit to the hackmd. I'll make this edit to it. So instead of this stuff, we could just do it. This was what view, right? Right. So now there's something I should have shown you guys, right? For every time we do scab build, right? For every time we do scab build, there is a folder that is generated called targets. And inside this target, when you come inside the dev and you come inside it, you see that we have a file that is being created, a JSON file. This file that is being created is the ABI, right? It's the ABI, and you can notice it has all the data about that contract. It can show you the name of the functions, the enums, the version, everything that entails in that contract, right? It's all in this file, this .json file that is created in this target and dev, right? So let's pay attention to this file here, right? Because it's from this file, whatever we get here, that would aid us when we are declaring and deploying our contract. Okay, so now that we've gotten that out of the way, the next thing we'd want to do now is to compile this contract that we've created, which is this simple storage. And I want you guys to pay attention to this target and this dev, right? To see what's going to happen when I compile, right? So I could just come to my terminal here and do what? Scab what? Build. So when I use cabid, are you seeing this? Are you seeing learn Starknet underscore simple storage contract underscore class.json? So this is to show us that it has generated the ABI that is required for our contract that we just wrote, right? So now when we are declaring and deploying, we'll make reference to this contract that we've created, right? So the next thing we're going to do now is for us to declare and deploy this contract, right? This process of deploying and declaring is what will help us to, it's what will help us to have this contract and have an access point through which people can make requests to either read or write. So I sent the link to the article and you can follow it. But that article is, let me share a link to the article for deploying so that it makes everything easier. Right? I have a better article here. This article is much more recent and it will help us in like understanding what we're doing. So I'll just share a link to it in the chat. Right? So now, so the first thing we're going to do now is for us to create the account we're going to use to deploy, right? This process would involve us making use of Starkly, right? And Starkly is a tool for account management and deployment. So for you to install your Starkly, you could just go to book.starkly.rs/install. So I'll just show you guys a link. I'll show you guys where to install it. You can just come here. You just see it here. So for you to install it, you could just do this, then you do Starkly up, right? So by the time you've installed it, then we can now move on to the other process of installation. So the first thing we are going to do when we are installing is for us to, create a folder to store our key store. So one thing you should note is that for you to be able to deploy your smart contract, you need to ensure that you have a Starknet account, right? Because that is the only way for you to be able to send a transaction to the blockchain. So what you are doing when you are deploying a smart contract is you are sending a transaction to the blockchain so that your contract will be added to the existing blockchain. So when it's added to the existing blockchain, you can now have access to it, right? So how do you perform this transaction? For you to perform this transaction, you need an account. And so you have to create that account. So lucky for us, creating this account to Starkly is super easy. We'll just, by the time you install Starkly, you could just you just come in here and we'll create a directory first. We'll call it mkdir./Starkly wallet. So I would recommend that by any time you create this directory, right, you ensure that you add it to your git ignore so that it doesn't push your private key along with whatever you're pushing to GitHub, right? So you could do it like this, add it to your git ignore, right? So that way, this is not added when you are pushing your code, right? So now we are going to move into using the stack. So now what you're going to do now, the next thing you're going to do is we're going to generate a new signer. So it's with this signer that would enable us deploy our contract and declare our contract faster. So what you'd want to do is that you'd want to create a new key store file. So what this key store file is, basically, it's a file that would store your private key, then encrypt that private key. So it will allow you to set a password for that private key that you are creating, right? So you're creating an account for deployment, and that account that you create for deployment, you are putting a password to that account. The key store file is a file that stores your private key, but we are encrypting that file so that even if we expose that file, nobody can be able to decrypt that file, right? So to do that, we're going to use this command, which is Starkly, which is what Starkly signer key store new. So new, we'll now put the direction of that folder that we created, which is Starkly wallet, right? Slash whatever. So if you notice in the Starkly wallet, it will now be inside the file which we call what keystore.json, right? Keystore.json. So we could just press enter. Yep. So it will ask us, it will prompt us for a password, right? So it's in this password. This password is what is going to, this password is what we're going to use to like lock our key store file, right? So I'll put a password for mine. Then you see that it has created a new encrypted key store file, right? This is our public key, right? You can copy this, comment it out somewhere, right? Comment it out somewhere. I want you to also note that this account is what? It's not yet deployed, right? This account that I created for us is not yet what? Deployed, right? It's not yet deployed. So we'd have to go through the step of deploying it. But another thing you could also do is to export. You'd want to export this your key store part, right? So to export it, you'd use this. So the reason why we're exporting this key store part is so that we don't have to write the path to this key store anytime we are deploying our account, right? Or anytime we're making any interactions. If not, anytime that we want to make any interactions, we have to write the full path, right? We write this path, which is user/this/that/Starkly wallet/key store. By the time we export this path, we now have a variable that stores the path to our key store file, right? So I'll just paste in the command here. As you can see, export Starknet key store, which stores the path to this our key store file, right? Then from there, we're going to initialize our account using Open Zeppelin's class. So to do that, Starkly is making this deployment and declaration really easy for us. We just use Starkly account OZ, which stands for Open Zeppelin. In it, then we'll put the link to this our account. So you could either put this part like I put it here, or you could put, I think you put Starknet key store like this, it should work. You just put Starknet key store since you've already defined that variable. But let's just go on like this. So you put in the password for your key store that you had put in before, and now you can see the new thing is telling us. It's telling us that once we've deployed this account, it will be available at this. For us to deploy the account, we have to run Starkly account deploy followed by the key store part, right? So we could just copy this again, then come here and do Starkly account deploy, right? It will ask us for the password, right, of our account, which we'll put. And then it will soon prompt us now to fund. Okay, so now it's showing this because if you look at the error is saying error sending request for URL, blah, 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 because the error is trying to connect. And so now the reason is because Starkly is making use of a public RPC URL, right? When we say public RPC URL, the RPC URL is the URL you are using to navigate or communicate with the blockchain, right? So the RPC URL that Starkly is using is a public one that almost everybody is using. So because of that, it makes it choked up with a lot of people that are making requests. So for you to solve this, you'd have to go and generate your own RPC URL. So to generate your RPC URL, you can go to alchemy.com, or you could use Infura, right? Either alchemy.com or Infura, and that's where you could go and you generate your RPC URL. So when you've generated your RPC URL, you'll be given an RPC URL. And so when you do that, you just come into your command, which is this Starkly account. I would want to clear this screen so that we could have we can have our so we can see our commands clearly, right? So now you put in RPC flag followed by the RPC URL you've gotten, right? So in my case, I already have an RPC URL. So I just copy my RPC URL and then I'll pass it after the flag, right? So I'll put in the password to my key store. And our account is about to be deployed. So, but look at what it now says. It says the estimated account deployment fee is 0.005 stack. To avoid failure, fund at least 0.01 stack to the following address, right? Which is the address that's generated for us. So what you'd want to do is copy this address. If you've got any Starknet Sepolia, you'd go fund it. But the best way we could just do this is to come and fund from the Starknet faucet, right? So to fund from the Starknet faucet, you do Starknet Vercel faucet. You could just search this online. So you come here to the testnet faucets. so you can see the Starknet Hackathon that I told you guys about, which is coming up May 26. I'd encourage everybody to participate. Break yourself into teams so that way you'd have a higher chance of winning because you'd have somebody else tackling each specific session in the application. So our transaction has been sent, and when we view our transaction, we can see that, let's just check it. We can see that what our account has been funded, right? So now that we've done that, we'll just come back to here and we can press enter since we funded the address. And you see account deployment transaction is waiting for the transaction. And once our account, it's taking a while, and our transaction has been confirmed. So what we could do is we could copy this transaction hash, come back here and search it just to be sure that our account has been deployed, right? Everything is transparent on the blockchain. You can see that this is the transaction. You can see the value it took. You can see everything, right? This means our account has been deployed, deploy account. So now we are going to move to the next phase of what we are doing, which is for us to what? Because remember, what we are doing essentially is that we are declaring and deploying our smart contract. So to declare and deploy our smart contract, there is a command in the tutorial that you copy, which is the Starknet declare. So remember in our earlier part, I talked about how you have to declare a contract first before you deploy it. So when you declare a contract, you get a class hash. And from this class hash, you can now keep on making deploys of that contract. You can make deploys of different types from that class hash that you've got. So this is the command. But now the difference is here, if you notice in this command that I copied, it's referencing target dev simple storage class.json, right? So what we'll check now is we'll ensure that this file exists in our own VS Code, right? So remember that last command has to be, oh, let me paste it here instead, because this is where we're doing it, right? That last command has to tally with the name of our file here. And our own here is what? Our own here is what? Our own is different, as you can see. So I'll copy ours and come back to the terminal here. Then I'll what? I'll replace it, right? I'll replace it. So once I replace it, I'll press enter. But okay, I'm coming. So if you notice, it's still throwing that RPC error, which means I still have to use the RPC I got from Alchemy or Infura. So I'll just go back and get my RPC from Alchemy. Node URL, copy it, come back, and paste it, and press enter, put in my password, and voila, we have our class hash. So it's waiting for the transaction. Has confirmed the transaction, and now we've gotten our class hash. So we can copy this class hash, come here, paste the class hash. I want to paste the class hash. Okay, it's taking a while because it has to update the data. Okay, so we can see our class hash now. Class is a template for a contract. You can see our class hash. Deployed contract 0 because we've not deployed the contract. All what we did is what? We declared the class hash, right? So now that we've declared the class hash, the next thing we're going to do is to what? To deploy the contract. And now to deploy the contract, we use another command. The command we're going to use now is Starknet deploy. So for us to declare, we use Starknet declare, pass in the key store and the account. Now we're going to use Starknet deploy. And we come here, paste that command. But in this case, we're using a different class hash, right? We're using our own class hash. Our class hash ends with 78C6. So we'll change this and we'll replace it with what? Our class hash. Then let's not forget to add what? Our RPC. The RPC followed by our RPC URL. I mean, I could just copy this one here that I used before, and then I'll paste it here and put in the password to my account. And our contract is being deployed. Oh my God, it's got an error. Error, 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 error. Oh, okay. So now the error we are having is because we are, our contract is taken in a constructor, right? So because our contract is taken in a constructor, we have to put in the right flag for the constructor, right? So how do we do that? How do we do that? How do we do that? It's coming. So give me a minute. So we also have to pass in the constructor argument. So we could just have our class hash. We're supposed to pass in our constructor argument. Our argument now. Let's say we put in what? We put in 10, right? And we press. So 10 is the argument that we want to go in first for our constructor. Right. So I'll try this again. Okay, so I did not pass in the argument properly. Just give me a minute. Let me solve this. I mean, a temporary solution for this might be to just give me a minute. So we just need to add an argument for our constructor. Okay, so I've gotten the constructor arguments we're going to use. So because it's a U256, we cannot just use regular argument like that. It has to be different. Yes, it has to be different. So for that, we'd want to, let me go back to the code, paste this. So the argument will be more like this. So immediately after our class hash, so with U256, it's broken into two U2128. So because of that, there will be both the high and the low, right? So the inputs would have to be something like this. So do okay. What? Two dashes. Okay, fail to create cells from string. Comment. So I'll just modify the argument a little bit. I mean, I could also just decide to, remove the constructor. Yep, we could just remove the constructor and remove the constructor. We'll just declare the contract again. When we are declaring our contract, it's just the same thing, right? But except that now we'd have to compile again. So I'm coming. I'll just do scarp build, right? Scarp build. Right. So by the time we've done scarp build, we should get a new simple storage, right? So now we could just do what? Declare again. Same account, right? We're declaring again. Put in our what? This. After we declared, then now we'll deploy again, right? For us to deploy now, right? So now I'll replace what the class hash now with the new class hash. Put in my key stop password. Right, so now our contract has been deployed, and this is the address to our contract, right? I could come here and check it out. Is there any questions? Nobody has dropped any questions. So I prefer to use Voyager. I prefer to use Voyager for most especially whenever I want to like interact and see how the contracts are. So with Voyager now, I could just come here, paste in the contract address. Look at the link. I made sure I use sepolia.voyager. Sepolia.voyager. So when I paste in the contract address that we just got, you can see that the contract was just deployed, right? It was deployed from the class hash and deployed by that our account, right? You can see that currently there has been no account calls. We have our read and we have our write functions here. If we call the original read, we won't get anything because like we haven't like written anything to the contract yet. But then now to set a value, we might. So it will require us to connect our wallet. We could use the cartridge controller and just to do a brief interaction, like has it done it? No. I want us to use the cartridge controller so we don't have to connect a wallet. Okay. Because my agent here, I don't know if I'm coming. Let me just I'll set up an account on my agent. I'll set up the testnet account on my agent now. I'm coming. So I'll just give it a little funding so that I can, we'll be able to like interact with our contract, because I want us to interact with it and see that the contract is actually working. So I'll send in one stack to my test account on my agent. Yep, so I've sent in one stack. So I'll share my screen now. I'll share my screen again so that you can all see my screen. So can you see my screen? So now if you look at my screen, you see that I've gotten one stack in this account, right? So now I want to interact with this. So I'll click on Agent X and it will show me a connect pop-up. I'll connect my account. And now I can just set a new value, right? I put set. When I do that, when I try to interact, you see that a pop-up will come up in our wallet here that would ask me to confirm, right? The fee is even paid by agent because it's like my first transaction. So thank you, agent. So you can see that it has done the transaction. I've been able to set a value, right? But how am I sure that this value has been set? I'll have to click on read contract to come and read it, right? And I'll query and I should be able to get the current value. Okay, our result is still returning this, but we've written into our contract. Let's refresh. It's currently still returning empty, but that means the problem is probably from our smart contract. Let's look at our contract. Or did that transaction not go? Let's try and write something else. Let's write like 1, 2, 0, 0, 0. Right, we've transacted again. Let's open this transaction hash. Let's see what happened. So you can see that we did this. We set value. We sent in this number. We convert to the raw transaction. What do we see? Decimal. We see that it sent in this thing and called our contract, right? So we can go back now to read contracts. Call query. Yeah. But our result is still returning empty. Probably because of the constructor information that we removed, right? So pretty much that's how to deploy and declare your contract. The next thing we're going to do, according to our tutorial, is we're going to, yep. So we've been able to declare, we've been able to deploy, and we've also been able to like interact with it, been able to call all the right functions. The next thing we want to do is so according to our we're going to just show how it is to initialize an event and how to also make use of a syscall, right? Because the syscall that we are going to make use of is how to like get our caller address, right? Which is like getting the user's address whenever. So one of the importance of using the get caller address is that the get caller address enables us to be able to, for example, want to implement things like access control. So to implement access control, you'd want to get the caller address and compare it with the original address that you set in the beginning of your contract, right? So because whoever is the owner would have, the owner's address will be initialized in the beginning of the tutorial, in the beginning of your contract. So you'd say, this is the owner's address, right? So once we've set our owner's address, the next thing we'd want to do is to, compare whoever is calling that function, how are we sure that the person is the owner of our contract? So just to do a quick implementation of this, permit me to comment this out. How did it comment? I think I figured out how we can deploy this our contract, right? So because we still have the class hash, right? We could just do Stackly. We could now do Stackly. We could do what? We do Stackly deploy, pasting our class hash, pasting the value we want to send in, like in this case, it's 100, putting our account. So putting Stackly slash, in this case, it's like this Stackly dash wallet / our account.json. Then we'll put in our RPC, which is this our RPC from here. Right, and let's run this and see. We put in the keystore password. And oh, we're still having the same error. So I think I'll figure this and I'll drop it on the Telegram group for us. Once I figure out what's causing this error. It's mostly with this Starknet tool. I'm passing in the right argument. Because we have to ensure that we get the argument data type right. So because it's U256, it's usually, let's look at the error. Oh, that class hash was not declared. Class with hash not declared. Let's get the right class hash. So this is the right class hash here. Send this C6. Let's see. So I even thought someone would have corrected me. I copied my contract address and not this thing. And not this thing. Not the class hash. With programming, you don't give up. If something doesn't work the way you want it to, you try it again until you can get it working. So now I put in the right class hash, but it's still showing failed to deserialize. So it's majorly because of the data type of that data we are passing in. So I think we should just move on so we don't waste time. We have limited time here. So the next thing we are supposed to do is to show how to implement events, right? And I said I was going to show you a contract, then add the events and show how like Syscalls also work here, right? So we have a contract like this. We have this contract. Right? And this contract, it's storage with events. We have our struct, we have our storage. It's an event that shows that the value has changed. We have events to show when the value has changed. We have the storage, we have the value here. And this event here is called whenever you set value, right? And whenever we get value, this event is also called. And there's only an event. You can see how the event is being called out here. It's called with emit, the name of the event, followed by whatever thing is being passed, which is old value and new value, right? So we have that set. And the event value chain takes in old value as unsigned is 256 and the 256 here. So this way we have a storage that is also making use of events. I'll make sure I push this repository, this Git, or I publish it to GitHub gist so that everybody could also like reference it. So now what we want to do now is for us to define a trait and also incorporate a syscall, right? So for us to do traits, you already know how to do traits, right? You know that anytime you want to add a trait to this stuff, which is the interface, we do what? Trait like this, right? But what's the first thing we do? We first of all make sure we get our what? Our Starknet what? Interface, right? Then we do what? Traits. Storage what with events, right? And then takes in what? T contract state, close it, then we have it, right? So we just get, I mean, the smartest way to just do this is that we just come inside here and we just copy this like this, copy this, paste it here, put a semicolon, change this to what? To T contract state. Then come here, do the same thing for the get value. And this time is what? T contract state. So right into this. And then we've got our traits implemented. The next thing we want to do is to incorporate a syscall, right? And one of the logical places for us to incorporate this syscall is in this set value, right? We don't want a situation where everybody can come in and change the value. So how do we do this with the syscall? We want to first of all ensure that the person who is calling the function is whoever is okay. So, or we could just make sure that whoever is calling the function is not a zero address, right? Not a zero address. So how do we do this? So yeah, I know that a zero address is 0x000000, right? That's like the richest address because every token that is being burnt is burnt to a zero address, right? So now that that is sorted out, so what we're now going to do now is we'll come to our set value here and we put it like this. Let our caller be equals to what? Get caller address. So get caller address is native to Starknet, right? Get caller address like this. But now the problem is get caller address is not easily accessible unless we import the necessary unless we import what is needed, right? And look at for events, we also have to import what event emitter because it's also necessary. So for us to do use Starknet, syscalls, get caller address. So for every syscall you are using, you'd have to like import it, right? Import it. So do get caller address. Did I spell this well? Get caller address, right? All right. When we've done that, we'll be able to get the caller address. And from there, we could now assert, like an assert, to ensure that our caller, which is the address we are getting, is not equal to what? 0. Else it should do what? Invalid what? Do what? Invalid caller. So if precision is equals to 0, it's what? Calls out invalid caller, right? Right. So time we do this, we should be able to ensure that it's the right caller that is making the calls, right? So I'm seeing that our recording is about to stop, but the recording hasn't stopped, so we're good. So by that, we'll be able to like show how to incorporate a syscall into our contract. So we will be stopping here for today because we've gotten to the end of the class, but so I would like to do a census. How many people want us to still go on so that we just touch one more thing before we go? Please react with a thumbs up. Okay, we have truths. I'm expecting to see Judith's thumbs up soon. Yes, okay, wonderful. So let's go. So now we're going to deal with cross-contract interactions and libraries, right? Set up a library and we'll try to implement that library into our contract, right? So let's just show how this works and we'll call it a day, right? So how do we define a library? How do we define libraries? So the libraries are defined without using the use Starknet contract, right? Or use Starknet interface or use Starknet component, right? So with libraries, for example, let me comment out this code. So with libraries now, we could have like what? We do what? Mode, let's say we are creating a math library, right? Mode math lib, right? Then we can now define our library. Let's say our library takes in a function to add and to subtract. So because I've written this code somewhere and I have like a boilerplate code, I could just come copy it and paste it here, right? And this is just like a regular Cairo program. You just taking a function, takes in two variables, it adds them and return it, multiplies and return it, right? But then we want to import this library into our contract. So let's say we have a contract like this, right? We have a contract like this. Right. So we have a contract like this. Same simple storage, you set value and you get value, right? But now we want to introduce this our math library inside. How do we get this math library that we've created to come into this our Starknet contract? So the first thing we want to do is to import it inside. So to import it, we use followed by the name of the library, right? But because it's outside, we'll use the super keyword followed by the name of the library, which is mathlib, right? Once we've done this, we've been able to import this library inside here. But now the next thing is we want to be able to make calls to it. And the perfect place to make calls to it is by coming to this place now where we have this, we are collecting two parameters, we're collecting A and B, right? So any value we want to add into this place, we want to make sure we add or multiply this A and B. What we could do is we could come, instead of writing A, or we could just do it like this, right? We do let's go A equals what? Mathlib, this is our library, right? We'll call the multiply function in our library, right? And then we'll pass in what A, comma B, right? Right, so we can now do self.write underscore E, or we could just copy it like this, paste it here. Let's use the add and see. Okay. So now, once we make this public, it should be accessible, right? Then we'll be able to like add it and add it to our contract. So when we're done, we've been able to show how to implement the math library. So because of time, we'll be rounding up, and we could always reference our, okay, I'm seeing someone saying we need more clarity about the creation of the wallet. So for the creation of the wallet, if you are using the Starknet tool, it makes it easier for you to create the wallet. What you are doing is that you are setting in your key store, and when you set in your key store, what that key store is doing is that it is storing the private key, right? It's storing the private key of your wallet, right? Let me open the keystore.json file for you so that you get what I'm talking about. If you come over to this Starknet wallet, right, and you see this account.json, and you see this keystore.json, what keystore.json is showing is, it's showing, so because it has encrypted it, right, it has encrypted it. If you go inside, it's supposed to show you the private key of that account you get. So that's what it's doing. So before we deploy this contract, the status of this thing would have been showing undeployed or not deployed, right? So, but with Starkly, we're able to like break it down into just simple key commands that make it easier for us. Let me show you. Let me open the article again and like reference it for what I'm talking about. So in the article, for us to create the account, right? With the first thing we are doing is that we're generating a signer. Then after we've gotten that signer is like our private key, right? Then we'll have to initialize the account before we deploy the account. With Starknet accounts, you have to deploy your account. That's why you see that when I created the smart account on my agent wallet, it said it was going to pay the first transaction for me, because what it was doing was it was deploying the account that it has created for me. That deployed account is a way of like instantiating and activating it. Similar to how maybe if you open a bank account, you'd have to make a transfer. They'll tell you that, oh, make sure you make a transfer, or make sure you get money paid into the account, so that it will be able to signal the system that this is an active account. You get that's similar to what the deploying of account does. Dakol Sati, have I made it clearer for you? Can you react with a thumbs up if you don't want to unmute your mic? Okay, wonderful. So I'd want us to like ask any questions that we've got, or if we need any clarity. I'll join the Telegram group now, and on the Telegram, my name is Otaiki Sedik. So you can go through the several documentations, the Cairo book, Starknet Foundry, Starknet by example. I'm open to questions. Thank you very much, and do have a nice day.